Last time we introduced a few extensions to our type system to start making it look like our normal language. But now there's a few things that our language has that we haven't yet integrated into our type system. So let's do those next. So the first thing is that we have pairs and other data structures. And then we also have boxes, so mutation. So let's handle all of those. So we're going to take our language E, and we're going to extend it so we have pair of EE. We're going to have first of E, second of E. We're going to have in left of E, in right of E. Actually, let's move that over. In right of E. And then we're also going to have case E of in left X arrow E, or in right X arrow E. And then we also need to have box E, set box EE, and unbox E. All right, so let's handle each one of those. Now we're going to have to integrate into our type system additional types to handle these new things. For pairs, we're going to call the type T cross T. For in left and in right, we're going to call it T plus T. And then for boxes, let's call it box T. All right, now let's look at each one of the rules. So the rules for pair is quite simple. We'll say that gamma proves that pair E1, E2 has type T1 cross T2 if gamma proves that E1 has type T1 and gamma proves that E2 has type T2. Then we'll say that if gamma proves that E has type T1 cross T2, then gamma proves that first E has type T1, and if gamma proves that E has type T1 cross T2, then gamma proves that second E has type T2. Now notice that pair is very similar inside of the type system to an AND, because what happens is with a pair you have to provide a T1 and a T2, and then you get to select either one of them. In left and in right are going to look more like an OR, where we'll say that gamma proves that in left E has type T1 plus T2 if gamma proves that E has type T1. Notice that T2 right here is free, meaning that it's undetermined what exactly it should be. This is actually a problem and would require a type annotation on this in left. So we actually have to change the syntax for in left and in right to deal with this. Where now when you write an in left, you have to have an E and a type, and when you write an in right, you have to have a type and an E. So we'll say in left E T2, because you have to say what the other side is supposed to be. Similarly, we'll say that gamma E has type T2 means that gamma proves that in right T1E has type T1 plus T2. Now the rule for case is the next one. So this is a bit complicated. Really, it's not complicated, it's just big. So we'll say that gamma proves that case E1 of in left X goes to EL, let's call it E2, E2, if, well, and, we'll say or, in right, Y arrow E3. Now here are the conditions. Gamma has to prove that E1 is a T1 plus T2. That's the first step. Then what we need to do is we need to say that if we take gamma and we extend it with a mapping from x to t1, notice that x is the left thing, then that has to prove that E2 has type T3. And we need one more rule. So actually let me just do a little bit of rearranging with our special paper. So we'll circle this. Let's move it up so we have some space. Okay. Then let's just take this and move it down a little bit. There we go. Okay, now we'll write the next rule in there. So the next rule says that gamma extended with a mapping from x to T2 also shows that E3 has type T3. Now notice what this means is that, like an if, both sides of the case have to return the same kind of thing. All right, so we've handled in left and right our cases. Now we've got to handle our box things. So let's do that on the next page. 24.2, so we'll say that gamma proves that if E has type T, then gamma proves that box E has type box T. If gamma proves that E has type box T, then gamma proves that unbox E has type T, which makes sense. Finally, gamma proves that setbox E1, E2 has type, should we have it be unit? Should we have it be like C? Let's have it be unit. It has type unit, which recall is like void. If gamma proves that E1 has type box T, and gamma proves that E2 has type T, because the thing that's inside of the box has to match the new thing that's going in. All right, so here are some new rules that handle the new features of our system, the other features of our system. Now, there's kind of an annoying thing about these rules and about our whole system in general. For example, just pause real fast. All right, so there's a few things that are annoying about it. Mainly, why do we have to write these functions at all? Because recall that with the lambda calculus, we didn't have to have pair and stuff like that built in. We could actually encode them using lambdas. The problem is that in our language, lambdas always return the exact same kind of thing. Here's a really good example of that. Let's look at this term in the untyped lambda calculus. Lambda x dot x. So this is the identity function. It can be applied to anything. So for example, we could take the identity function, lambda x dot x, and apply it to 5. Okay? Then what we could do is we could take the identity function and apply it to plus. And then we could apply these together, and then we could apply that to 5. And this program is going to run and produce 10. Because when we send the x into the plus into here, we get back a plus. When we send the 5 into there, we get back a 5. We add those together, and then we get 10. Now the problem is that in the typed lambda calculus, we can't write down, i.e. in our typed language, we can't write down these two terms. We would have to write this one as lambda x, which is a function that goes from number to number to number x. And over here, this one would be lambda x number x. So notice that we have to write two different versions of the exact same thing, depending on whether the type should be number, arrow, number, arrow, number, or whether it should just be number. Now this is really unfortunate because it means that we have to duplicate lots of code in our program every time we need to use it on a different type. Now, in languages like Java and C++, there are features that allow us to avoid this. For instance, Java has generics, and C++ has templates. For example, in Java, I could write a function that would be like, I could have a class that was called the ID class, and it was parameterized over an x, and I could say that it had an x, which was the thing, and then I could write ID takes in x t, and we say this dot thing equals x, and then these are public. Okay. Then I could instantiate this at ID number, or I could instantiate it at ID, cat, or ID image. And so this exact same code can work on many different kinds of types. It would be really nice to have this feature in our language. Well, how can we write down this feature? This feature, by the way, goes by the name of polymorphism, which is Greek for many shapes. So the way that we represent this is by changing our language by introducing a new expression form. The way that the new expression form works is that we have what's called a type abstraction. So a type abstraction is the place in your code where you say, inside of this block, there is a new type, and we don't know what it is yet. Now, because lambdas are the thing that gives us value abstractions, a type abstraction is going to be a capital lambda, and a capital lambda is like it's like an upside down V. And we give it a type variable x and then an expression. And then we can take one of those things and we can take an expression and we can apply a type to it. So this is like a function, but it's a function at the type level. And this is like a function application, but at the type level. And then we extend the set of types to include a new kind of type that's called for all x e. And then we also have a new kind of type, which is a type variable. So for example, what we could do is we could write down a single typed expression that was like the identity function. So here's the untyped version of the identity function, and here's the typed version of the identity function. We would write capital lambda, and now by tradition we write type variables as Greek letters. So we'll write alpha, and then we'll say lambda alpha f, x is of type alpha, return x. So that right there is the identity function. Now, what is its type supposed to be? Its type is supposed to be for all alpha, it takes an alpha and returns an alpha. So what are the type rules? What we're going to do is we're going to take our type rules and we're going to change the definition of gamma. Our old definition of gamma was essentially that gamma was equal to either nothing or a gamma plus saying that x is of some type, and then that's it. What we're going to do is we're going to add a new thing for gamma. So it's going to be those things, plus it's going to be one more thing, which is just to say that x is a valid type. All right, so now let's write down the rules. The rules for polymorphism say that gamma proves that big lambda xe is of type for all x t if gamma, when we tell it that x is a valid type, that proves that e is of type t. Next, we'll say that gamma proves that E applied to type T is a certain type if gamma proves that X is of type for all X T2. So we'll call this T1. Now what we do is we're going to say take T2, find all of the X's, and replace them with T1. So let's look at a concrete example of this. So a concrete example of this would be if we take the identity function and we apply it to number, and then we try to call that with 5. Okay, so how does this work? Well, the first rule that we'll do is we'll use, so we're trying to prove this. So this right here is an application. So we need to first prove that 5 has some type, and its type is number. Okay. Then we need to prove that ID of num takes a number and returns something. And whatever it returns is the thing that's going to go there. Okay, well that right there is a type application. So that means that we have to prove that ID is of type for all X something. Well, let's look at what it is. Well, ID is a for all, so that means that we're going to use this rule. So that means that we're going to say that if alpha is a valid type, actually, the name is going to be alpha here. If alpha is a valid type, then we want to prove that lambda alpha f x is of type alpha x has some type. Okay, and what is that? Well, it's a lambda, so that means that we're going to say that alpha is a valid type, x is of type alpha, and then we have to prove what type x is. And we're going to discover that it's of type alpha because of that. That means that this is a function that goes from alpha to alpha, which means that this is for all alpha, alpha hour alpha. And so what is this equal to? Well, it's equal, it's equal to alpha arrow alpha, where we find all the alphas and replace them with number. And that is, of course, equal to number arrow number. So this takes number arrow number, it gets number, so therefore it returns number. So thus we can see that ID num5 is going to be a number. All right. Now, one thing that I neglected to talk about is what these things mean at runtime. What does it mean to actually do this? So, for example, what is the rule? What happens when you run a type application? Here's one way that we could do it. One way that we could do it is we could say that there's a new category of value, and the new category of value is a lambda x v. And then we could take our evaluation contexts, and we could say that you can do lambda xe, so you can evaluate inside of there, or you can evaluate inside of a type application. Okay, then what we would do is we would add a rule that said if you're inside of a context and you get a big lambda xv, where you're applying that to type t, then what you should do is you should go inside of the v, find all the x's, and replace them with that type t. So what that would mean, for instance, is that if we started with ID num 5, then the red x is going to be that, because this is of course equal to big lambda alpha lambda x alpha x, okay, and then that's applied to number, and then that's applied to 5. So this thing isn't a value. This thing is a value because that's a value inside there, so that means that we go and we reduce this by finding all of the alphas and replacing them with number. So we would get lambda x number x. And then we would have the 5 there, and then that would run and become 5. This rule right here makes sense, but it also kind of doesn't make sense. And the reason why it kind of doesn't make sense is that notice what it means is that at runtime, while the program is running, we're manipulating the names of the types. So we're going and we're finding all of the x's and we're taking them and we're switching them to be something else. But what type something is has no bearing on how it runs. It's a prediction about how it's going to run. So basically what that tells you is that there's no way for this substitution to be meaningful. So from that perspective, one thing that we could do is before we run the program, we could just go through and just erase all of these. We could basically like add a step to our language that basically said, anytime you see a big lambda in it, just delete it. And anytime you see a type application, just delete that and then just run that program. The problem with this, however, comes down to what happens if the same value is applied different ways. So imagine we wrote this program. We wrote let ID equal equal big lambda x, we'll do alpha. Big lambda alpha, lambda x of alpha x in, and then we wrote if ID true, ID 3, ID 4, and I just realized that I made a big mistake because I got to actually apply these. So it's going to be applied to ID bool true, and it's also going to be applied to ID number 3, and let's just leave this 4. So if we just go through and we erase these, so we erase that big lambda and we erase these type applications, well, what happens is that now we have a function whose argument is alpha. Now in the theory, this doesn't matter. It's not going to cause any issues. But of course, if we're actually coding this in practice, well, what exactly are we going to make it like down at the lowest levels? This x right here is going to take a certain amount of memory to store. So that means that when we call this function, it's going to anticipate that value coming in, whether it's a true or a 3, in a certain amount of space. And how do we know how big that space is going to be? There are basically two common strategies. Strategy 1, basically what it says is that polymorphism assumes arguments are pointers. The reason why it assumes that they're pointers is that if we assume that they're pointers, then that means that they are word-sized, And that means that no matter what the object is, the pointer to it will be the same size. So if I have a single number sitting somewhere in memory that's only 32 bits, well, the pointer to it is 64 bits. But if I also have a 700 megabyte database, well, the pointer to that is also 64 bits. So by pushing everything behind a pointer, that essentially makes it so that all of the objects are exactly the same size. Thus, we only need to compile once. Only compile once. This is the way that Java generics and corresponding features in C# work. It's a very common technique. Strategy 2, however, says make unique copies for every type. So, for example, with this program right here where we apply it to bool and we apply it to number, essentially what happens is we transform the program into let id underscore bool equal lambda x bool x in id num lambda x num x in if id underscore bool true and then id underscore num 3 4. So what we do is we make a separate copy of the code once for each time that we instantiate the object. Sorry, once each time we instantiate it. This is what C++ does. So C++ is defined as doing this. So C++ has to work this way. There's lots of reasons why C++ has to work this way. One of the main things is that you can write instantiations of a template that are totally different depending on on what the type is. So what I mean by that is that with Java, if I write list of x, or maybe we're writing a set library and I write set of x, well, no matter what x ends up being, the code will always be exactly the same. In contrast, with C++, I can make it so that set of int works differently than set of cat, which works differently than set of bool. For instance, maybe if I want to do a set of bools, I'll represent it as a bit mass, which will be very efficient. So one of the consequences of this is that C++ compilation tends to take a long time because every time you use a template, what we need to do is we need to go look at the implementation of it, copy that into your file, change all the type variables to be whatever types you apply to that, and then recompile it. So basically what that means is that if you use 3 template libraries, then you're going to be compiling those. So essentially C++ code, it's difficult to ship purely binaries. You often need to ship the implementation, i.e. the source code as well, so that it can be instantiated with whatever types the user tends to provide. And if you look inside of C++ object files, it literally makes names like this. It uses a complicated encoding scheme that's not just putting underscores in front of them. But if you were to look at an object file, you could see exactly what types a class was instantiated at. It's not obvious that either one of these is better than the other. Strategy 1 certainly makes compilation faster. It makes it so that the code size is smaller. But it also can be less efficient because it means that the code is not specialized for what kind of value is actually there. Similarly, strategy 2 does have the downside of making this so that things compile longer, but it has the advantage of being able to take advantage of optimization opportunities on a per type level. So there's no correct way to do it, is my point. All right. Do I want to say anything more about that? Yeah, let's say one more thing, which is that once we have polymorphism, there's this concept that's called parametric polymorphism. And here's the idea. Imagine that I told you there was a function called f, and its type was for all alpha, alpha arrow alpha. Okay, that's what its type is. Now, I'm going to tell you that you are going to call f, you're going to instantiate, so you call f of number with 42. Okay? Now, what number comes back? So think about that for a moment. Before you jump to an answer, think about an alternative function called g, and its type is number arrow number. And you called g of 42. Could you tell me what number comes back? Well, g could be this function. So g of x could equal 0, in which case 0 would come back. Or g of x could equal x, or g of x could equal x plus 1, or g of x could equal x times 4. Okay? So you don't know. You have no idea what value comes back. In contrast, if I tell you that f's type is for all alpha, alpha arrow alpha, you know that the answer that comes back has to be 42. And the reason why it has to be 42 has to do with the typing derivation. So let's look at how we could end up with the type being for all alpha, alpha arrow alpha. How is that possible? Well, let's start off with no types, and we're going to have lambda, big lambda, a of something. Okay? Let's call that E1. Well, now, E1, its type, it's going to know that alpha is a type, and E1's type had better be alpha arrow alpha. Okay, because that's how this happens. We're just going to put for all in front of whatever comes back. Okay, so now what does E1 have to be? Well, the only way that E1 could end up with that type is if E1 were a lambda. And in particular, it has to be a lambda that says that there's some variable that takes in an alpha, and then that's E2. Okay? Because that's the only way that there can be an alpha there. So that means that when we go inside here, it's going to know that x is of type alpha, and we have to show that E2 returns an alpha. Now, what are the different ways that we could get an E2? Here's one way that we could do it. We could have it be x. Here's another way that we could do it. We could say, if true, or really any expression involving a Boolean, and then we'd have to come up with an expression that's an alpha and another expression that's an alpha, which is actually kind of the same thing. It turns out that these would have to also be x eventually, and this would have to also be x eventually. The only value that we know about whose type is alpha is x, because we don't know what alpha actually is. We don't know that it's number, so we can't write 42. We can't write 7, we can't write x plus 5 or anything. The only thing we know about it is that it's some type. So what this means is that polymorphism provides a security channel. Here's an example. Imagine that I am selling the service of being a safety deposit box. It would be really bad if you put something into the safety deposit box at the Bank of J, and then I could go in and change it to be something else. You thought you put in a 42 and you'd like to come back and get a 42. But actually when you go in, it's a 43 and it's something different. Now, I would only be able to do that if I knew that you put a number in your safety deposit box so that then I could go in and change it to a different number. But if you give me something that is like hermetically sealed and I can't look at it, then as if I'm following the contract that I return the same kind of thing that you gave me. If I don't know what kind of thing that is, then there's nothing that I can do to it. All right? Now, unfortunately, actually, let me step back one step. So, like, what's an example of this being useful other than for the identity function? Well, the map function, its type is for all alpha, for all beta, it takes an alpha arrow beta function, and it takes a list of alphas, and it returns a list of betas. So what this tells us is that this function right here, it's not only going to be called with only numbers, let's say. It's also only going to be called with numbers that are actually in this list. Because map can't possibly know what type alpha is, so it can't fake any other values. Similarly, this list of betas that comes back has to be betas that actually came out of this function, because map doesn't know what beta is, so it has no way of faking it. Now, unfortunately, polymorphism, as it is implemented in Java and C++, does not provide this feature. So Java and C++, and other languages too, like typed racket, don't provide this. And here's the reason why. I'll give an example in Java. In Java, I can write the following. I can have a class that's called ID that is parameterized over X, and it has X, T, and it has the constructor takes in an xt, where I say this dot t equals t, and then let's imagine that there's a function called get that takes no arguments and returns x. Now I can write the following in Java. I can write if t instance of cat return Garfield, else return t. So because of the instance of operator, I can look at values and ask what kind of thing it is. And once I know what kind of thing it is, then I can do stuff to it. C++ has the same feature, and so does typed racket. But languages like Haskell and ML do provide this. And it's a very valuable property for reasoning about your programs, because you know what kinds of things they're going to return. All right, so that's enough for today.